സാർ ജോയിൻ ചെയ്തില്ലേ? അഗ്നസ്
ജോയിൻ ചെയ്ത് സർ ജോയിൻ ചെയ്തിട്ടുണ്ട്. പാർട്ടിസിപ്പൻസ് ജോയിൻ ചെയ്തുകൊണ്ടിരിക്കുക. ഒരു ഇൻ 5 minutes നമുക്ക് സ്റ്റാർട്ട് ചെയ്യാം.
താങ്ക് യു. ഓക്കെ, താങ്ക് യു. രണ്ട് ഡിപ്പാർട്ട്മെന്റ് ആയിട്ടല്ലേ?
Especially our speaker, Dr. Joseph V. Thanikal. The webinar and it is actually organized by the Department of Civil Engineering in association with Institute of Engineers, India, Jyothi Engineering College. And a few instructions before the commencement of the webinar. I request everyone to kindly mute yourself and switch off your videos. There is a live streaming of the webinar in our YouTube channel, and every participant will be given an opportunity to interact with the speaker. And if you have any queries, you can post it in the chat box towards the end of the session, and which will be asked to the speaker once the session is over. So I request everyone to kindly cooperate. Thank you so much. Now I invite Alina Sajan to introduce the speaker for the day. Yes, Alina, over to you.
Hello everyone, and welcome to today's webinar on Wastewater Management Overview, organized by Department of Civil Engineering, Jyothi Engineering College in association with Indian Institute of Engineers. At first, I would like to introduce our Honorable Resource Person, Dr. Joseph V. Thanikal. He is currently working as Associate Dean and Director of RICS School of Construction, Amity University, Noida, India. He has more than 35 years of academic and research experience in engineering and research institution. He has been consultant for industries and for many organizations. He has obtained his basic engineering in civil engineering and specialized in environmental biotechnology. He was awarded postdoctoral fellowship from 2003 to 2005 by National Institute of Agriculture Research, Laboratory of Environmental Biotechnology, France. He has over 80 publications at international journals and was also awarded patent by World Intellectual Property Organization for inventing technology for highly concentrated industrial wastewater. He is a member of Canadian Council of Professional Engineers, Canadian Environmental Practitioner in Education and Research by CECAB, Society of Chemical Industry, SCI. He is a chairman of Specialist Group Small Water and Wastewater Systems. He is a distinguished fellow and executive committee member of International Water Association, and he is also a member of IWA COVID-19 Task Force representing India. He is life member of Indian Society of Technical Education. Sir, we welcome you and it is an honor to have you here. I also welcome our faculty coordinators and our student coordinator to today's webinar. Finally, I invite all the participants to the webinar. Hope you like it. Now let's begin our session. Over to you, sir.
Thank you. I just would like to check my audio is clear for everyone.
Yes, sir. Your audio is clear. You can present your slides.
Just trying to. I haven't done a webinar on Google Meet, so kindly help me.
Yes, sir. Yeah, sure. So what you can do is you can see a present now icon in your
Okay.
Google. So just click on present now, and then you will have an option for sharing your entire screen.
Okay.
So you can click on it, and then you can open up your PowerPoint presentation or PDF, whatever is you are willing to share.
All right. Okay. So is it visible now?
It is not visible, sir. Yes, it's coming, sir. Yes. Yes, now you can open your, now we can see your screen. You can open up your presentation. Yeah, so you can put it in slide mode and start presenting.
Yeah, is it fine?
Yeah, it's visible. And to the participants, you can just pin on Joseph Lee Thanikal presenting for for viewing the PowerPoint which is shared. So you can present your PPT.
Yeah, I'm just trying to do that.
Yeah.
Okay. So hopefully my presentation is visible, right?
Yes, it's visible. Yes.
Okay. So thank you, Alina, for the kind of introduction. And I need to remember Professor Siriak, who's a good friend of my father, they both have been working in Kerala Water Authority. So that's how Professor Siriak has invited me for this lecture. So, sir, thank you for inviting, because I consider these are the opportunities where I can share my expertise with the students. So thank you very much, and thank you, Agna, for sending me the invite. Uh, just to give you a broad outlook of what I'm going to do today is,
Uh, Sir, just 1 second. Can you put it on slide mode? The presentation.
is that fine?
Yes. Thank you so much. Yeah.
Okay. So I'm to speak about the wastewater management and wastewater treatment as it's to the students, and I understand that you already have done the water treatment, or about the water management. So, and I understand that you are stepping to eighth semester, so you have a basic knowledge of civil engineering. Uh, if I'm to talk about the wastewater treatment and its management, it's a huge subject, a very wide and very vast subject, but I don't think we'll be able to do it in 1 hour. So what I'm trying to take you through is some of the fundamentals of the wastewater treatment. And then I'm going to present you two experimental studies that was completed as a part of an Indo-French funded project. So to give you an idea about how these things basically work at a laboratory level as well as at an industry level. So with that, I would conclude my presentation. And then after that, you have any questions, I would limit myself within the boundary of my knowledge to give you an answer. So moving on to the next slide. So first of all, before going into the wastewater as such, I just would like to give you an idea about what is called as a built environment. So all these belongs to a built environment. So when you take built environment, there are quite a lot of things which are involved in built environment. So we talk about anything in built environment, and what is the challenges that we face is because of the human activity. So while we have these activities, the question is, can we spare the activity, or can we not have this activity, or should we continue with the activity? So you have to continue with the activity as a part of the development, but at the same time, we need to understand that we don't cause any pollution or any damage to the built environment. So if you look at the built environment, largely to understand, you have a real estate, construction, and then infrastructure. Now that includes land, building, planning. You also have energy, communication, transportation, urban and rural infrastructure, and social and commercial structures. So all these put together is what we're talking about built environment. So by that, we understand that it's a very small part that we are planning to discuss today. So it's a very simple and small part that we are going to discuss today in this particular session. So my first question is that why do we have to treat wastewater? So there are different things that comes to your mind, or if I'm putting this question to any of these students here, then they will come up with a lot of answers which has been listed here on this. But I'm more interested in the last point, which has been said here as a solving social problems. So what are we trying to do is that we are, with the built environment development, we are causing a socio-economic issue to the environment. So the very important thing that we need to do is to have a balance of socio-economic issues within the society. And that's the reason that I said that I'm more interested in saying solving social problems caused by accumulation of wastewater. So to what extent we are able to do, and to what extent we are able to resolve the issues, this is in our hands. And as planners, as civil engineers, as architects, all those people, they need to really think about how how important is the wastewater. Now, wastewater is basically that emerge out of use of water. So when you understand that it comes out of use of water, then how meticulously and how clearly you can plan to to use water so that you can reduce the quantity of wastewater coming out. The regulatory systems in India has not gone up to the state, unlike in Europe, that they are charged much more than the cost of water on the wastewater. So you'll be really surprised to see that when you waste a drop of water, it is costing you much more than the drop of water that you have used. So they're very conscious, and also they are very reactive to this situation that the wastewater is very, very minimal. So that is ultimately the achievement that we need to do. You would have heard the word called zero discharge, but zero discharge still remains on the design or in the paper, but still practice, it has still not been achieved. Now, what is exactly this wastewater where it's going to be there? Either you put it on land or you discharge into the water body. Both have got microorganisms and ecosystems that protect the environment. So the impact on this is very high because when you throw the wastewater on land or wastewater or in the water body, you really have not studied what are the kind of microorganisms that exist in both the locations. So thereby, what happens here is that some of them die, some of them will grow, but some may be favorable for the environment, some may not be favorable for the environment. So basically, you will have these issues because without knowing what you are discharging and without knowing the characteristics of the wastewater that you are discharging, you will end up with problem and then spoiling the complete ecosystem or the microorganisms which are present in the soil or in the water. So, what is the ultimate aim of the wastewater? So, one is that you manage wastewater. So that, as I said, like you try to use the maximum water. That means use it as a reuse. You can have recycling before you convert that or you call it as the wastewater. So that means ultimately you cannot use that water, and that's the reason you are throwing it out on this. So that is called as the wastewater management, and that also leads to what we call it as the life cycle management. The other one is what is called as the wastewater treatment. Now, it's pretty clear from here is that, or single word is that we don't want to pollute the environment, and that's the reason we would like to treat the wastewater. Now, when it comes to wastewater treatment, at one point there are a number of technology which are available, and now what technology to be used. So if my technology is going to be expensive, then I might stay away from treating the wastewater and then just throw it without treatment. So it's again the choice of treatment methodology or treatment technology, and then how effectively you try to adopt one particular technology for treating the wastewater. So it's a little big, a larger diagram or a larger perspective of the wastewater treatment. And this is more or less, if you look at the wastewater treatment and water treatment, the treatment stages are more of the same, or you will see similar stages in this case. So to simplify the whole diagram, there is an input And I would say that there is something that the mechanism which has to happen in between to get an effluent, which is benchmarked against the standards of disposal. Now, between the inflow or the input and the output, what happens here is the technology and how well we can manage that to have the output with the minimal cost for the technology as well as the best effluent quality that will not spoil the environment. So there are methodologies by which you can have this particular treatment, and there are technology which are available on this. So basically, you can have a biological system and you can also have a non-biological system. In the non-biological system, the challenge that you will come across is that the effluent need to be further treated to again comply with the standards before you dispose. But mostly with the biological systems, it has got less damage or less things to be done after the treatment, and then you will have this particular effluent quality. So looking at that, probably the technological part, you will have to decide on what is that we need to take up for the treatment of wastewater. So if you look at again the wastewater distinction between within the wastewater, how you divide this. So one is the domestic wastewater and the other one is industry wastewater. The main thing that distinct between the domestic wastewater and industrial wastewater is mainly the COD, the chemical oxygen demand, and that will be more for the industrial wastewater compared to the domestic wastewater. Similarly, if you look at the suspended solids, this can be the same or this can be a little more for in case of the industrial wastewater, but depending on what procedure and what product that they use in the industry. In domestic wastewater, you could see that the standards are much different from the industry wastewater. So that is where both the characteristics of domestic wastewater and industrial wastewater differs. So if you could look at now the industry wastewater, there are more of toxic metals and there are trace elements, trace metals, which are a challenge to be removed, or the treatment become more expensive while you try to remove these products. But as far as the domestic wastewater is concerned, it is basically the solids which are to be removed, and also your COD and BOD that requires to be removed, which are generally can be done with a simple biological process. But as far as industrial wastewater is concerned, you might have to look at a combination of the chemical treatment, physical, chemical, and biological treatment. So this is just to give you an overview of what we are talking about in the domestic wastewater and industrial wastewater. So there are three treatments which you already know. As I said in the water treatment, it's the same thing that is applicable here also. So you have the primary treatment, and you know that why we use this primary treatment is to remove as much as the solids that can be settled by gravity, and then you try to go for the process by adding chemicals or any other, the liquids. Thereby, you can form the flock as well as you can form the colloids, and then you try to settle them at the bottom of the tank. And there is, if you consider this for the industry wastewater, what we try to do is also supported with the equalization tanks, wherein the industry effluents are maybe more with acidic in nature, so you'll have to bring it into the base or alkaline nature for adopting any kind of treatment methodology. So the first part is the primary treatment, and that is where you try to remove the solids. So while you remove the solids, there are two processes that is happening. One is that you are trying to reduce the BOD, and also you're trying to remove the COD. And if you look at largely at the international publications, if you look at, the main focus will be on removal of chemical oxygen demand. And so how much you can reduce, or the efficiency of the wastewater treatment is considered on the basis of what percentage of COD that has been removed. But it again matters from one place to the other place, or depends on what kind of treatment methods that you use. But largely you can say that we are trying to reduce BOD and COD before you discharge this on land or on water. If I have to, as I said, that the biological processes are more safe, and also it's less expensive, and the maintenance of which is also comparatively less. So we'll be seeing now the biological wastewater treatment, how these things can be done. So if you look at, there are two major types of treatment. One is called aerobic, and the other one is called anaerobic treatment. And while you do this anaerobic or aerobic treatment, again, that can be divided into suspended and suspended treatment, suspended growth, as well as the attached growth. So we'll be seeing in detail with an experimental part, like how do you see the suspended growth and the attached growth here. So suspended growth is that you keep the entire wastewater in suspension, so that the particles, the solid particles, they will come in contact with the microorganisms which are there in the system or in the wastewater. So these are called aerobic bacteria, which can survive only in the presence of oxygen. Okay, so you have the suspended growth with an aerobic system. So you need to keep the liquid in suspension, and that is achieved by method called aeration. So you blow air inside the treatment tank, and then you keep the entire system in floating, and thereby so in suspension, and thereby you give an opportunity for the bacteria to come in contact with every single particle which are there in the system, in the wastewater. The other one is that we allow, or we try to put some media, and this media will help the microorganisms to get attached and then grow on this media. And the wastewater will be under a flow, and the wastewater will come in contact with of these surface on which the bacteria are attached, and thereby the reaction takes place, and then gets the wastewater gets treated. So that is the difference between a suspended growth, and the other one is an attached growth. So attached growth is basically, we call it as an anaerobic system, wherein the bacteria are more of anaerobic in nature, which is, we call it as a methanogenic bacteria. So in two cases, what is acting on the wastewater is the microorganism, that is the bacteria. So hence these are very sensitive organisms, so that we need to maintain a typical condition inside the wastewater so that these microorganisms survive. So the first one, in the aerobic system, you need more oxygen to be supplied, so which may be got from the air, or if you require, you need to supply additional oxygen for the multiplication of this microorganism. At the same time, in the anaerobic system, there should not be a presence of oxygen for them to grow. Okay. Now, how does these microorganisms grow? They take the food, or they consume the food from the solids which are there in the wastewater, and then they try to survive. So there need to be enough food for the microorganisms to eat and then multiply. Now, what is the sensitivity in both the cases? The sensitivity is that you need to have alkaline media. That means the pH should be above 7 to see that these microorganisms survive in the wastewater. They survive and multiply in the wastewater. So I think you got a better background of what is an aerobic system, anaerobic system, suspended growth, and the attached growth. So what I said now is the biological treatment. This is what you will see. So the suspended growth, that will maintain the the organisms and the solids in suspension, and then they come in contact with this. All right. And what is the process that is happening here is that will help and convert this waste or the solids, what we call it as the activated sludge. Now, why do we call it as activated sludge? This sludge is basically with the microorganisms, which are the aerobic bacteria, which comes out as a part of the treatment. In the attached growth, as I said, we need to provide a media or an inert material onto which the microorganisms will get attached, grow, multiply, and then treat the solids. So aerobic and anaerobic system, which I've already said to you. So if you look at anaerobic biological treatment, so in which the pollutants in the wastewater, that's the organic matter, are stabilized by microorganisms in the absence of molecular oxygen. And the other one is in the presence of molecular oxygen. So in the activated sludge process, you could see that the oxygen is supplied, and then it helps the microorganisms to grow in the treatment tank. Now, when can we apply the activated sludge system or the aerobic system, and when can we apply the anaerobic system in the wastewater treatment? So when you apply aerobic system, then you will have to see that the suspended solid concentration is low as not more than 6 grams per liter. So that's where you can see that the activated sludge systems or aerobic system will work. In the case of anaerobic system, this can be more. That means it is measured in terms of the COD, and it can go up to, in normal cases, you can go up to 10 grams of COD per liter. And there are industrial effluents which has got much more than that, in which case you need to have a dilution before you apply the this kind of methodology. So what is happening in the aerobic system? So this is a microscopic view of what are the kind of the particulate matter or the sludge in the form of all the solids which are there in the aerobic, in the wastewater. So you could see here on how these are found existing in the wastewater. So you could see that there are disrupted ones. These are the second ones are the connected ones. And then you have larger particles. And then here you can see that these solids are bound by protozoa. That's a simple blue line that you are able to see, and the microorganisms which are holding them. And here you can see also these particles are again held by the protozoa and the other microorganisms in this case. So what is happening here is on the left side at the in the left bottom corner, you see a larger particle that is there, and again there are microorganisms attached to that. All right. So what happens is that if this kind of particles are available or are there in the wastewater, then you can see that except the larger one, all will remain in suspension. All will remain in suspension. This will not get settled. So the idea here is that by injecting air at a high pressure into this, it not only passes oxygen, but also will try to break down this chain into smaller particles. Now, once they are into smaller particles, the aeration will support them to, then again, if you have to, then if you use the methodology called coagulation, then all these shredded particles will come in contact with the charges, with the positive and negative charges, and they'll form bigger particles. And then some of them will settle down at the bottom of the tank, which can be removed very easily. But otherwise, these particles will remain in suspension in the primary treatment. So we need to have this understanding in the primary tank that as much as the solids that can be removed by settling in the gravitational tank, that we must be able to remove. So just by a natural gravity process, these particles will not get settled at the bottom, for which you require a pressurized aerobic, the air injection to see that these things are broken into small particles, and then apply coagulant, and then try to bring down the particles before you apply the aerobic treatment. So that I'll just show you how does these things actually look like in any of the domestic wastewater, which enters into a treatment system. This is one of the latest technology. Earlier, we used to have an aerobic system which is spread over the entire land, or where you require more land. So this is an aerobic system, and the aerobic system has got 4 stages. So if you spread it over land, it's going to be occupy a larger area, and thereby, it occupies. You require a larger land to have the aerobic system. But now this has been consolidated into a simple tank, and this you have one tank, and the volume of the tank can be designed according to what we call it as the quantity of the input or quantity of wastewater that needs to be treated. So there are 4 major cycles, which is called fill, react, settle, and then draw. So draw means you draw the liquid, the treated liquid out of the SBR. So what you do here is that the first one is that you fill the tank to the optimum level of that, and then after that, the reaction stage, you can see that the air is pumped from the bottom of the tank, and this will keep all these particles under suspension for a designed period of the SBR. Then the next one is that here you stop the aeration and you allow the system to settle down. So you could see that now all these particles are settled at the bottom. All right. So you have the liquid that is in the tank, and in the first case, what you do here is that you remove as much as water that can be removed from there. Okay. So what happens to then at the bottom of the tank? So as the level of the sludge increases, and there's a mechanism that it automatically will reject those excess solids, and that will be mixed into the primary tank where it is filled, so that you get the sludge activated with the microorganism, and then you can see that the treatment efficiency is more. The entire system can be automated, and it is automated system. So you can see that once you have installed this particular system, you could see that it automatically works. In a sequencing batch reactor, the cycle is called 24 hours. So 24 hours, the reactor period is about 60% of the time is planned for aeration, that is the reaction, and then the remaining is for the settle and then draw, and then very less time for the fill of the system. So in 24 hours, you can, depending on the characteristics of your wastewater, you can even have 2 cycles or up to a maximum of 4 cycles you can operate this. So it depends on how well you aerate and how well you get the things settled down. Okay, and then you are able to operate maximum of 4 cycles per day in such kind of systems. So you are seeing a simplified system, which is called a sequencing batch reactor, which has been consolidated to a small tank. So this is one of the systems which I had worked in France when I was during my postdoctoral fellowship. So there was a patent which was designed for this, and this was again commercially produced by a company, and which was supplied to the cheese manufacturing industry. France is famous for cheese manufacturing, where the wash water in the cheese making industry, which contains the suspended solids, very fine suspended solids, and milk particles, which had to be treated, and that's where we try to use these small systems, which can be automatically operated. You don't require manpower to look at this kind of systems. So this is how it looks, and the person on top of the tank, you can see it was me. I was doing the sampling. So this is called as the northeast part of the France. So what I'm trying to show here is that it can be a tank on the left side that can be ready-made, and on the other side, you can see that it can be also built in concrete. And very well, very efficiently, and very easily that can be constructed and managed even in our Indian environment. And I've seen that there are many plants which has come up with it. So the unit that you're seeing on top of that is the completely automated one. And by sitting at home, you can always control this kind of treatment plants. So very efficiently used the sequencing batch reactor. So you can either construct or you can have the ready-made ones. Now, what is the theory behind both the cases? So in the what we call the suspended growth, and also in the case of unattached growth. So the theory behind here is that the film that you see, the biomass in the system, in this case, you will see this line over here, and then you are trying to see when you pass the oxygen into this part, then you will see this, the organic nutrients, and then the biomass is here within the treatment system, and that this will always remain in suspension. But whereas in the case of an attached growth, you need to have a surface on which you need to have you need to allow, or the microorganisms has to get attached and then grown on this. So probably, all materials, the microorganisms will not stick, but so to some materials, you can see that inert media, you can see that the microorganisms get attached and then grow very efficiently. So the material of an inert media is very important in case if we are going to use for an attached growth. So I'm trying to show you now the ones which I had used in my studies. So on the left corner, what you see is with the honeycomb kind of tube, which is made out of PVC. And just above that, what you're seeing is it's a polyvinyl material, and these are loosely packed materials. So this is a structured one, and this is a loosely packed. So the two inert media that you can use is that one is a structured one, the other one is a loosely packed one. The second stage, you can see that this has become this original color, an original one. So when you put it in the wastewater, and then after some time, you could see that they get converted into this color, the black one. So that means there is a coating of the biofilm. But whereas here, you could see that it's not only the biofilm, but also you can see that the sludge is getting trapped within that particular, we call it as a support, and then you can see that it's getting attached. On the bottom, on the last right corner, you can see that it's a magnified one. You can see that inside that tube, you can see that the fins, the thickness of the fins have increased. So that means these are the deposits of the microorganisms on this surface. The top one is this particular support. After oven drying, you can see that all that you see here on the support is the biofilm. So what we look at is that how much the area of or how much or the quantity of biofilm that can get attached to an inert media, and then what is the specific activity of this microorganism on this particular biofilm. So that depends on says the efficiency of the treatment system. So when you say 80% or 85% or 70%, that indicates that how much is the specific activity of the microorganism from the attached surface. So what you see on the left side, the 2-1, is this is not the moon surface. Please don't misunderstand. This is how a biofilm will look like under a microscope at 100 micrometer. So it looks very sandy, and this is the actual microorganism layer, which is basically acting or reacting with the solids to reduce the COD and BOD. So it'll be surprising when you try to see them under the microorganisms. So probably if you take a treatment unit, and in which, as I said, the previous supports that you put on the inert material, and then you try to have the microorganisms, you would see that at the bottom of the reactor, or what we reactor is a treatment plant, you can see that there are less of the microorganisms, but towards the top of the treatment plant, you can see that these supports has got more kind of the biofilm attached to that. So this is what I said. What is the gram per support, the micro and the solids which are attached. Now the problem that we encountered in this case in two of these one are, though you are seeing in the honeycomb one the thickness is more, but it has got very thin biofilm, because first time what happens here is that you get the mineral coating on the PVC surface before the microorganisms could get attached. So that indicates that they cannot get directly attached to PVC material. So thereby you lose quite a larger amount of area of the mineral coating. But whereas in the case of the polyethylene material, you can see that that mineral coating is not there, and thereby you get 100% the biofilm, which is more active than what you have seen in the PVC one. All right.